Okay. Electron withdrawing groups, on the other hand, recognizing these. The atom that is directly bonded to the pi system is either going to have a really strong partial positive or a full positive formal charge. Right? So again, carbonyl over here, this carbonyl that's bonded to it, carbonyl carbon has a strong partial positive charge. The one that you saw in the quiz, I don't know, there was an alkene out there, had a nitro group. That nitrogen has a full positive charge, right? So it's electron withdrawing. You can always draw resonance structures. What I would really love is for everybody to be able to sort of reason through, see some weird group they've never seen before, draw resonance structures, get to it. That's a lot to ask at this stage. I don't mean to insult your hand, just a lot to ask. You can quickly get it just by looking at the atom that is bonded to the alkene, right? So here we have an alkyl group. That's going to be weakly electron donating. This double bond actually has two alkyl groups bonded to it. Di-substituted. It's moderately electron rich, and it can do that. It does that reaction really well. If I take cyclohexene and I add HBr to it, under the right conditions, I'll get cyclohexyl bromide. Works nicely. The middle molecule with the oxygen on it, that alkene is so rich that it's acid sensitive. If there's even a trace of weak acid around, that thing reacts. The bottom reaction, like I said, this one down here, you essentially can't do this reaction. You cannot protonate that double bond. Okay. So I'll put some examples. Basically, this one over here, kind of like what you see over there. Really, any carbonyl. The important thing here is a carbonyl. Carbonyl bonded to a pi bond. That pi bond's not electrophilic. Cyano, nitro. You get the idea. So again, for the reactions in chapter 8 where the alkene is being a nucleophile, and that's all of them except hydrogenation. Right? Hydrogenation, I think it was last night at the review session I sort of said something about it. Hydrogenation is just a bizarre reaction. It doesn't fit in chapter 8 very well, except, things are adding to the carbon-carbon double bond, but it's not electrophilic in any way. Right? The H2 is not being electrophilic. And so, again, not that I'm going to cover it because it's not related, but the rate of reaction for a hydrogenation pretty much just goes with sterics. The more sterically hindered the pi bond, the slower it reacts. But all the other reactions in chapter 8 and chapter 9 for alkynes, all this stuff still applies to an alkyne just the same. If you put an electron donating group on the double bond, it's going to react faster in chapter 8. Put an electron withdrawing group on it, it's going to react slower. Okay. Questions? I didn't pep you guys up. All right. This will get you going. This will be good. Murmurs of worry I hear. Consult my notes. So right now this is open book, open note. All right, so it's a synthesis problem. I'm asking you to make this carboxylic acid from this alkyne. I'm going to actually put up another synthesis on the other side there So if you think you get an answer here, or if you're just completely stuck, you try the other one. So all the carbons in the product have to come from that Alkene. So that's a pretty common limitation we put on you in Orgo 1 and 2. I see some long face. Well, I can't really tell. I can only see half your face, right? But it looks like the beginning of a long face. So let me give you this, and it'll pep you up. I said this in the review session last night too, so those of you there won't pep you up so much. There will not be a synthesis problem on exam 3. This is preparation for, there is a doozy of a synthesis problem on the final project. Well, there's like, whoa, that's a really hard one, and then a doozy, and then also a doozy that just has less points to it. So I keep failing to pep you up. Sorry. And you'll see the answer in another video. Anybody want to say hi for, wave for posterity here? Yeah, all right. No, some 20, 30 years from now, Thanksgiving with your kids.